Hi, my name is Calvin Pierce, and welcome to my Comp 3132, Assignment 3. In this assignment, we're going to be learning about convolution networks and how they work and how they run. With that being said, let's just get straight into it. I'll try and keep it about as short as possible. So, first things first, we're going to import our necessary packages and libraries. Thankfully, Python makes this super easy for us. We can just use a lot of their libraries, and it just makes it overall just easier to read and understand. And then what we're going to do is we're going to want to get our image from the internet. As you can see, we're trying to get it from this link right here, and we're going to print the content of our image. As you can see, a whole lot of it looks like gibberish to us, but that is how the computer understands it. So what we do is, using NumPy, we want to transform that content into an array of values of 0 to 255, representing the color channels on the computer: red, green, and blue. And so, as you can see, we'll plot the image, and this is the original image. As you can see, it's a Lamborghini of some kind. I'm sorry, I don't really know cars, but it's a nice looking Lamborghini. And that is what we will see on the internet if we go to look at the image. So first things, what we're going to do is we'll print the shape. As you can see, it's 140 by 30 by 359 and by 3. And we can compare the values of the color channels, and they are not the same, as you can see. And then we're going to save color channel 0 in our input array variable and print it. As you can see, what we do is we actually change that last value in the RGB, which I believe is the G color channels, and we set it to 0, and it creates it like this image right here. And then we can visualize the values inside. As you can see, a lot, 255, which means it's kind of like maxed out. And then we're going to get into the convolutional parts with 2D kernels. So what we'll do is we'll create our array, once again using NumPy, just to make things easy for us. And we're going to create our kernel, and we're going to have our output array, which is just the same shape as our input array, but just filled with zeros. So as you can see, we've got that. And then we're going to apply our kernel, which was this up here, to our array values. And we're going to print our output array, and voila, now we got a white Lamborghini. Very nice. And then we're going to use some standard convolution. You can see this is all pre-written for us in the template, I guess, for the assignment, but it's nice just to run through it. You can kind of look at it, get an understanding of what it means. So this will have a function since the resulting arrays can be negative or greater than 255. So it basically says if the value is under 0, return 0. Otherwise, if it's greater than 255, return 255, or just return the value if it's in between those. And then we're applying our kernel to the image, and here is a nice little chart that's been provided for us with some of the convolutions to look. This is the one to look for horizontal lines, vertical lines, and then 45-degree angle and 135-degree angle, which is just an obtuse 45-degree angle. And if you don't know what obtuse means, it's basically an angle larger than 90 degrees. So you would have 45 degrees, which is smaller than 90 degrees. It's half of 90 degrees. And then 135 would be adding that 45 degree into an open 90-degree angle. Just to try and give you a visual representation of what the 45 and 135 degrees are. So next, what we're going to do is we're going to have a horizontal kernel. As you can see up in here, this is how it's created within the convolution. And we're going to apply it using that function that we made above to our original image. If you remember, it was that Lamborghini. And we're going to say the kernel we want to put onto the image, aka the filter, for when we're going to the convolutions to look at the chunks, if we're doing this horizontal lines filter. And we're going to plot the image. We're just going to be using gray when we plot the images, just for visibility purposes. It just makes it a little nicer on the eyes, a little easier to understand. You don't have to include that if you don't want to, but just for simplicity's sake and readability, we're going to keep that included for all of our images. Just thought I should make that disclaimer right now. And so moving on to the actual questions. What we're going to do is we're going to want to create that 45-degree angle kernel. And as I talked about earlier, it's just an acute angle of half of 90 degrees. And so what we're going to do is, using that little cheat sheet up here of the convolutions, we'll get our 45-degree angle, and we put them all in here. As you can see, it's the 2's. They kind of form the angle itself. If you think of it like this, the actual ray is 90 degrees going around the outside, and the angle 45 is all the 2's, so it would be kind of like that if you tracked my mouse movement. I'm sorry, a little sloppy, but you get the point, hopefully. And what we're going to do is we're going to apply that kernel into our original image, and voila, we are tracking all the 45-degree angles on the image. And then we're going to do the same thing with 135 degrees. You can see it's a little less sharp, but it still is a good job. It's still getting the job done. We got our right here. So the way basically I like to think of it is, for the 45 degrees, we looked at it like this. If you follow my mouse, that's our angle. We're going to flip it so that, like, this is starting at 180 back to 360 degrees, and that goes through there. Well, not 180, but this is 90 degrees going to, I guess, 180 degrees, sorry. And then we go through there, and that'll be 135 degrees. And so we're applying that to our image, and we get this beautiful one right down here. And now moving on, we're going to apply a couple more edge kernels to our image. And as you can see, this is our first one. We've got, it kind of just shows you a little bit of the weighted lines. You can faintly see them. We got our second edge kernel right here, which makes the inside of it is kind of blurred, but all around is good. And then we have a focus on the interior on our last one, and as you can see, it really, I guess, the word I'm looking for is bolds or sharpens the outline and the lines of the Lamborghini. And so that is just the quick little part A. It gives you a little bit of convolutions and a little bit of edge detection and line detection, a little how-to. And then part B, we're going to get more into neural networks and what we have been doing mostly for the course. And so we're going to import our packages and libraries again. Once again, I just had to, just a quick fix that I had to do. For some reason, it wasn't recognizing keras.utils, so just had to do tensorflow.keras.utils import to categorical. Otherwise, it should work, but it wasn't in my case, but it's just easy, quick fix. Just mentioning it in case one of you guys run into a similar problem. And so what we're going to do is we're going to load the data set. We're going to one-hot encode our target values. We're going to normalize our target values, and we're going to build our model. This has all been provided for us. As you can see, we got our one convolutional layer, a max pooling layer, a flattening layer, and two dense layers, one being ReLU and one being softmax, which goes into our output labels, but I can get onto that in a minute. And then we're going to compile our model using atom optimizer function, and we're just going to display this summary. As you can see, we got our 5 layers right here. And then we got our callback. This is just to give you a little bit of insight and information into the epochs as we're doing the training and as the neural network's going through the learning and going through the cycles. We're going to call this just so that we know it's still going. It's always nice to know because they do take a while. I recommend changing your runtime to GPU, which I can show you after I show you everything, just in case you guys don't have it done. Otherwise, this might take you a little while to run. Hope you got the patience. But we're going to go into train our neural network, and this is how the one provided for us performs initially. So as you can see, we got our 50 epochs, 256 batch size, our callbacks, which is just letting us know, hey, we finished epoch 0, which is the first epoch, which is the first loop through our neural network, and the training accuracy is such, and the validation accuracy is such as well. So on and so forth for the entirety of our epochs. And then this right here is just to plot our data. As you can see, we've got our training data and we've got our validation accuracy. So our training accuracy is very good. It keeps on going. It's so close to 190, we'll say 97, some odd. And then we got our validation accuracy, which kind of going with it, and then slowly creeps off until we get to about epoch 10, where it kind of just flattens out and kind of stalls and even starts to get worse there at the end. And so going on to a couple of questions from the assignment is, did the network present signs of overfitting? Yes, it did. As you can see above, our validation actually stalls out around epoch number 10, and that is where our network kind of starts to overfit, because although our training accuracy is getting better, our validation accuracy fails to improve, or even if it does improve, it's so minuscule that it really doesn't matter. And after that, it just stalls out, it doesn't really improve, and that is where the overfitting takes place. And then, like I said earlier, we do have our 5 layers. I can scroll up and show you. Let me just go up a little more, sorry. When we do our summary of the model, we have our 5 layers: a convolutional layer, max pooling layer, flattening layer, and our 2 dense layers, this one being ReLU and this one being softmax, with our 10 output labels for our data set. And then, what is the purpose of the layers? Well, the purpose of all the layers are as follows. The convolutional layer takes the image and looks at it in small chunks. So we have it in 3x3 chunks. It'll start at the top left corner and go on, so on and so forth throughout the entire image, changing the height, the width, and the depth. Most important of that being the depth. And it looks at it in small chunks. And then we use max pooling, which looks into those small chunks that our convolutional layer created, and it says, hey, this is the max value within that chunk. I'm going to take that value. And so what it does is it actually technically shrinks the size of the image, but it is still storing kind of the same essential data that we need in order to read and view the image. For like, if we looked at it, we could still be like, oh, that's a 4, for example, because it takes the strengths and the highlights of the images and really just kind of highlights them. And that's how it works in relation to the convolutional layer. And then next, we have our flattening layer, which converts our data to a 1D array so that our neural network can easily learn from it. And then we have our dense layer with our ReLU activation function to zero out all those negative values if we have. And then finally, our softmax layer, which is our output probability layer. And it basically just says, this belongs to this label right here. And then what we're going to do is we're going to want to add another convolutional layer. So I added one right here. I actually increased the size to 64. And we still want our max pooling layer because we still want to take the max value from that. We're going to flatten. All this is still the same. Run our epochs. And I'll show you this little data right here. You can see the accuracy is a little better. And we get the result. Boom. So we're at about 70%. If I scroll up to this one, you can see around epoch 10 we're at about 64%. So it is a little bit better. We're getting about a 6% validation accuracy increase, which is pretty good. Not outstanding, but it's pretty good. And basically it does that before it starts overfitting as well. Since we have the 50 epochs, we're going to be overfitting every time. But for the purpose of the assignment, it's nice to have for the visualization. So as you can see, our validation accuracy, it actually improves. This is about the same mark, which is right at the beginning, which is about where the validation accuracy kind of starts, I would say. It's about epoch 3 or something. Don't quote me on that. But as you can see, it learns a lot quicker and a lot faster and thus more accurately. And now we're going to add a dropout layer. So we have our same model as before with our 2 convolutional layers, our 2 max pooling layers, and we're going to add our dropout layer after our flattened layer, but crucially before any of our dense layers. And basically, we're going to, I'll show you the data and then I'll explain how it works. So we'll run our compile, our fit. As you can see, our epochs, the training is actually very good on it. As you can see, the validation accuracy is actually really good. It goes up very quickly, very accurately, very fast. And so, like I said, I was going to explain the dropout layer. I got a little writing down here for you. So basically the purpose of the dropout layer is it randomly zeroes out some of the output features during training based on the number that you put up here, wherever my dropout layer is right here. So that's about 50%. There's 25. You can do whatever. But 0.25 or 0.5 is kind of the go-tos, I would say. And basically, what it does is it keeps the neural network fresh. Consider it like an athlete training, for example. When you stop training, you begin to get out of shape, you begin to get lazy, and all that. But when you keep on going, you can say you keep on training every day and you get a new task thrown at you, your body is still athletically fit. It can go and easily or more easily achieve that task than if you were just not doing anything and all of a sudden this athlete was asked, hey, try and do this new task, and he's out of shape, out of training, all that stuff. So basically, it keeps it fresh. So it drops out a value and it makes it work and find new creative ways to kind of solve the problem and get around, hey, why is this 0? So it keeps it fresh. It keeps its problem solving skills up to date and more accurate so that it can prove better on the unseen data. And as you can see, it's actually very good on the validation data. We still get the overfitting, but like I said, we're running so many epochs that overfitting is going to happen. But the accuracy that it achieves so quickly and so fast is very good and very cool. And then lastly, we're just going to try and improve the accuracy just a little. So we're going to add another convolutional layer, and we're going to keep our dropout, and I'll show you some of the results there. Sorry, my computer's just being a little slow. Just a little frozen, I guess. And whatever, I'll just continue talking. When it comes back, it comes back. Basically, there we go. We got our accuracy curves. As you can see, it is very good. It learns very quickly, very steadily. It still gets around the epochs, this time around number 12. But it's learning quick, learning fast, learning efficiently, and kind of everything that you would want from a neural network. So as you can see, just using the various techniques, such as adding extra convolutional layers to increase the accuracy, adding dropout layers to increase problem solving, and how it looks at new data is very important and can improve our accuracy and our data and our neural networks. Also, while keeping our validation accuracy really high at the same time, keeping it fresh and ready to go for new unseen data rather than just trying to memorize what it has already seen. And that concludes my assignment. Thank you for watching.